Dr. Len Losik presents his discussion on Air Force satellites and rockets' premature failure and how to prevent it to 200 naval postgraduate officers who will be assigned to the National Reconnaissance Office. The NRO purchases more satellites and rockets than any other government agency, and consequently, they suffer the most failures of any U.S. government agency.
Dr. Len Losik is with us today to talk about the spacecraft reliability analysis.
Thank you. Welcome all. Thanks for coming. And we've been given the opportunity to film this session. The NPS is the only organization, institution that's been allowed me to actually film it. All the companies and different organizations and conferences don't allow such a thing, and so that's why we're taking this opportunity to do that. Thanks again for coming. And what I'm going to talk about today is spacecraft reliability in a sense. My connection to the space industry goes back to the GPS program back as early as 1978. I was the guy who was physically sitting on the council with the GPS program officers, telling them which atomic clock to operate. At the time, we were competing against two Navy satellite-based navigation programs called Timation and I can't remember the other one right now. Timation and
Transit.
Transit, yeah. And so we were able to beat out in terms of functional performance the GPS program, which much better performance-wise than either of the two existing Navy satellite-based navigation programs. And done launch vehicle design, spacecraft and launch vehicle factory design, test, launch and on-orbit operations for a multitude of commercial, NASA, as well as military space programs. And so what I'm going to be talking about today is a new paradigm that we're pushing for spacecraft reliability. Currently, what's used in the industry is a probabilistic reliability number, often referred to as a piece of S, and that's dealing with reliability of equipment and vehicles as a roll of the dice kind of thing. And so what we want to do is change that to one where we're going to physically measure the reliability of equipment. We're going to measure the reliability in hours, days, months, or years. And that way you're going to be able to identify what the duration of remaining life of the equipment. And then for the ones that's going to fail prematurely, we'll have an opportunity to remove those while they're still on the ground and replace them with equipment that won't fail prematurely. And so the purpose of my visit is to introduce you to this new paradigm in reliability, getting away from a probabilistic or possibility of success or a probability of success and a probability of failure, which actually allows, the way that the reliability requirements are written today actually allows equipment to fail prematurely. When you're dealing with probabilistic results and you've got equipment that's failing prematurely, it's okay because the reliability requirements are specified such as a 90% probability of success or a 95%. That says that allows 5% or 10% to fail. And when they're specified in that way, now it allows equipment to fail prematurely. And so what we're pushing for is that the reliability of the spacecraft equipment be specified as a duration of remaining life. That is, how long is the equipment going to operate? In the case of a launch vehicle, we're actually pushing for a mission life of 1 year, that the equipment will need to operate in a launch vehicle that's only got a functional use of about 30 minutes. But to ensure that none of that equipment is going to fail prematurely, we're pushing to have that reliability of the onboard equipment 1 year. And so it's quite a change paradigm. And so I'm going to be also discussing prognostic technology, which is the tools that are used to be able to measure equipment reliability versus dealing with the roll of the dice kind of probabilistic results. And I'll also be discussing the two most recent satellites that were launched by the Air Force Space Command. One was a new classified communication satellite referred to as the AEHF Advanced EHF communication satellite, a geostationary satellite, and the latest GPS-2F satellite. Both of them failed prematurely. The AEHF satellite, which is the communication satellite, the apogee engine didn't function. It wouldn't stay on continuously. That satellite, the Air Force was had such low confidence in the builder, who happened to be Lockheed Martin up in Sunnyvale. They directed Lockheed to test the satellite completely twice, hoping that what happened on orbit wouldn't happen, and it happened anyway. The GPS-2F satellite that was just launched, the satellite, one of the payloads, the nuclear detonation detection subsystem, wasn't interoperable with the existing satellites on orbit. And so I'm going to tell you today how that can happen, how it is that the Air Force can procure the equipment that fails prematurely, as well as how the builder can build equipment that fails prematurely. To begin with, I'm going to talk a little bit about how often space vehicle equipment fails prematurely. And it's tied in with the Orbital Express mission, and that's why I'm talking about this. This chart here is meant to just talk, the red is the number of satellites per year that failed over since 1959, that failed prematurely within the first year of use. And all this, the actual numbers aren't important, it's just to show that every year since 1959, a small group of satellites failed prematurely, unclassified satellites for the military. And the more satellites that are made, the more that fails prematurely. This is a chart that's almost unreadable, but these are for launch vehicles, for the U.S. launch vehicles, the Russian, European, Japanese, etc. This is the number, this is the percentage up here that have been successful. And you can see 100%, and you can see about 10 or 15% of U.S. launch vehicles prematurely, and likewise for all the different countries. I'm going to elaborate on this data in just a little bit. This is just a summary. Using game theory to understand launch vehicle and spacecraft reliability. This is kind of a new application of game theory. What these are called learning curves. And when a guy decides to sit down and write a video game, he's interested in knowing how difficult should he make it. These graphs are effort on the bottom versus results. And this is just a regular learning curve. This would be a shallow learning curve. This is a steep learning curve. And this is a learning curve that is created when you can build on your experience. This is a curve where there's virtually no learning curve, learning that's necessary. We call that being able to use intuitive reasoning. This learning curve, there's 3 different programs here, 3 different video games. If you learn how to play this video game here, then you can use it on the next video game and the subsequent video game. And that's sort of the way that people that play video games would like it to be. You learn how to play one very good, and you'd like to be able to use that skill that you learned on one to be able to play another one. This one here is a chart just showing the results with no learning curve whatsoever. And so this is the information that's really important to understand reliability, effort, again, versus results. This is data that's produced by Aerospace Corporation, and this is for launch vehicles. Every launch vehicle that the U.S. has produced since 1956, and including the Russian launch vehicles here. Both operational launch vehicles as well as historical launch vehicles. And I just wanted to show you, these are the learning curves for these launch vehicles. Mind you, some of these launch vehicles have been produced and used for up to 50 years. And the best that they can do is roughly about 90%. And so, what these curves here, the fact that every launch vehicle, even the shuttle, where's the shuttle at? Even the shuttle had one of those learning curves that was on the previous chart. This indicates that absolutely no experience was used from one launch vehicle program onto the other. When a vehicle, such as a satellite or a launch vehicle, has a learning curve, a learning curve at this size, which matches the initial learning curve that was on the previous chart, it's indicative that no experience was used. And that means that the Air Force was never ever, the military was never able to share the experience among launch vehicle programs. We can do the same curves for the standard product lines of satellites and spacecraft that companies now produce, dating back to the early 1980s. The spacecraft have the satellites that are used, that are often sold for military applications, produced by the dozens and dozens, share the same kind of learning curve. And again, that's indicative that we're not able to share experience from programs. Although the company's name is failure analysis, we don't do failure analysis. We went to the next step. We're not interested in doing analysis for equipment that failed. We're interested in now in stopping equipment from failing prematurely altogether. We want to stop, we want to have contractors produce equipment that will not fail prematurely. We believe that the space systems are too expensive and too important, to fail. And so the technology that we offer now is a result of understanding why equipment fails in the first place, so that you can eliminate those failures from occurring in the future. Also in today's lecture, I hope to get the opportunity to explain to you why the tools called failure analysis and root cause analysis are the wrong tools to use when you want to produce equipment that won't fail prematurely. This is a chart that was developed by Aerospace Corporation. Back in 1990, they published a report trying to justify the extreme cost of testing satellites to begin with at the factory. And what they did was they took a look at 60 satellites from a variety of suppliers. They went through the factory testing, and what they found out was that for those 60 satellites that they ran through factory testing, now mind you, this is with equipment that's from suppliers that has already passed the dynamic environmental factory accepting test program. That's the shake and the bake, the vibration, let's see what else, acoustic, EMI, electromagnetic interference, electromagnetic compatibility testing, all of those things that are done at the factory to try to make sure that whatever is produced won't fail prematurely, that it will be able to meet their mission lifetime. And what they found out after this equipment came from the suppliers, arrived at the vehicle integrator, they found that of all that equipment per satellite, per every single satellite of the 60 satellites, every satellite that went through factory tests suffered 4 mission critical failures. And what they used this data for, this 4 failures, they said, well, if these 4 failures hadn't been found in factory tests, they were going to occur on orbit. And so that alone justified to Aerospace Corporation expending the money to test the factory, to test the equipment while it was still on the ground, so that some of the stuff would fail prematurely, so it wouldn't occur in space. And then what they found was, for the 60 satellites that they ran through and compiled this data from, only 47 of them got actually launched into space. They had to produce the report, so they weren't able to track the 13 of them didn't get launched by the time this report got published. What they found was, of the 47 that did get launched into space, there was still a 70% chance of having a mission critical failure within the first 45 days of arriving on orbit. The one thing that they didn't realize with this 4 critical failures, mission critical failures that occurred, what this meant was, it meant, remember, this is equipment that hasn't gone to space yet. This is still on the ground. This hasn't received the dynamic environment of a launch vehicle and the shock from separation and things. This is equipment while it's still on the ground. They fail to recognize that when you've got 4 units failing per satellite, that the factory test process is inadequate. If you're producing equipment that fails prematurely before it ever gets to space, there's something wrong with the process. And that's what they failed to recognize. They just assume that equipment as complex as this, whenever you work in this environment, it's got to fail prematurely for whatever reason. And so they didn't ever come to the conclusion that the factory test process is the problem. This is a chart. This is called a Weibull distribution curve, and this here is used to understand. This is failures in time, and this is over a 10-year life of a complex system such as a satellite or an aircraft, really any complex system. This chart shows the rate of infant mortality failures, equipment that fails prematurely on a complex system over a 10-year period. The red dots are the infant mortality failures. The blue dots are the normal lifetime failures. What we did, we said, well, if you can eliminate infant mortality failures, now mind you, some of these infant mortality failures actually occur because you replace some of this equipment over here that failed prematurely, and then some of that failed. And so you have this long period of infant mortality failures. We said, well, if you eliminate infant mortality failures here, you are producing equipment with 100% measured 100% reliability. Okay, since equipment reliability is dominated by infant mortality failures, you get rid of infant mortality failures, you're producing 100% reliable stuff, and that's what we're trying to get to. And so what we did was we were able to come up with it's called prognostic technology, and you were able to identify the equipment that's going to fail prematurely by searching the test data with very specific algorithms. And so what we did is we used prognostic technology in order to search for what's called transient behavior. And in the space industry, you do not recognize transient behavior. The aircraft industry does. It's often called a cannot duplicate, or no failure found, or no failure identified. Well, in the space industry, we don't recognize transient behaviors as occurring. And I'll explain to you why that later on. But by identifying the equipment that has transient behavior in it, you replace those with equipment that doesn't have transient behavior in it, and you get equipment that won't fail prematurely. And over the last 30 years of doing this, we developed an accuracy of predicting the remaining usable life on space vehicle equipment, satellites and launch vehicles, within 5% accuracy. We have 5% accuracy bars on our remaining usable life. When you start producing equipment that's not going to fail prematurely, the flight history of that equipment becomes less important. Currently, the part of the data that's used in developing the reliability analysis results includes flight history. Has this equipment ever been used before? And that's, has these parts ever been used before? That data goes into the calculations that's required as part of the reliability analysis engineering. When you do this process, flight history no longer is important to reliability. And so our approach for stopping satellites and launch vehicles that fail prematurely was we discovered the presence of transient behavior. In other industries, these are called prognostic markers, prognostic identifiers, failure precursors, or accelerated aging. We concluded that the factory acceptance test program was inadequate. We then discovered that all measurements taken during factory testing, everything that's taken during factory testing is performance related. That means that there's absolutely no measurements taken that have anything to do whatsoever with equipment reliability. All of the measurements taken on equipment at the factory is performance based. How well is it working? If you've got reaction wheels, are they spinning at 2200 RPM? If you've got an RF transmitter, is it putting out 3 watts? If you've got a 5-volt line, is it remaining at 5 volts? All of the measurements are performance related. That's why equipment has been failing prematurely, is because none of the testing that's done in the production of equipment and vehicles for acceptance testing is related to reliability. And so we said, if you want to identify how long the equipment's going to last, you have to develop a measurement that defines the remaining usable life. And that's what I'm here about. So we developed the algorithms that identifies the accelerated aging or the prognostic markers in the test data. And from that data, we can then calculate how long the equipment's going to last. Our ability to identify equipment that's going to fail prematurely is only valid for the first year. We have not, over 30 years, been able to see equipment behavior indicating it's going to last more than a year. So this analysis that we do is valid only for the first year of use of equipment.
Sir, when you say we, I think Boeing?
No, a failure analysis, my company. Okay. And other industries that use this technology called prognostic technology. It's used more generally in the consumer or commercial industries. We're trying to bring it into the space industry in order to increase the reliability of spacecraft and launch vehicles now. Telecommunications companies, nuclear power has been using it for 30 years. We're just the first company that developed the algorithms for the dynamic environment that happens inside satellites and launch vehicles. It's very dynamic. You got equipment coming on and off automatically, and that causes transient behavior in the data. And so we developed the algorithms to differentiate normal occurring transient behavior from the transient behavior that indicates the equipment's going to fail prematurely. And as far as we know, we're the only company to do that for spacecraft and launch vehicles.
So just to clarify that last statement,
yes.
So you're saying for a satellite that's got a 10-year lifetime, for
yes.
instance, you can, with your predictive approach, determine that you're going to be okay, you're going to have, in essence, 100% reliability for the first year of operation.
Right. And then what you do is you do the analysis again from the data from the satellite, and that analysis is invalid for the next year. Okay. And so what that means for on-orbit satellites, if you're doing this analysis that we offer, is you can identify the equipment that's going to be failing up to 1 year in the future. And so you can then, instead of having suffering from surprise equipment failures, which often put the equipment at risk of total failure, you can manage those equipment failures to a positive conclusion. Quite often, equipment that's going to fail prematurely, once it's identified, if you change the conditions that it's operating in, normally the temperature environment, it can extend the usable life of the equipment. It also offers you an option to turn off the equipment that you know is going to be failing and turn on the backup equipment so that you won't have any interruption in payload services, for instance. And so we've suggested to the NRO that the NRO has very poor on-orbit reliability for their satellites. They're always either they're not getting up into space or the payload's being turned off because they're having so much premature equipment failures on orbit. This will allow them to be able to predict what their space asset's going to be for the next year, the space asset availability, with great certainty, where right now it's strictly the equipment failures that occur that takes the satellite data offline. It just happens sporadically and randomly. And so we've suggested that the NRO use our ability to do this so that they can, when you're doing strategic analysis of, as Strategic Command does when they're trying to figure out, based on the threat environment and what assets are available, it's kind of important to know what space assets you got in the next year so that you can, do that plan. And so that's what our technology offers for on-orbit satellites as well. So this is just a test plan for the TT&C subsystem, just trying to show you, and these are the different tests that are done in the acceptance test program, showing which measurements are taken in which tests is all. But these are the kind of measurements that's taken for the telemetry commanding subsystem. Range loop stress, a performance measurement. RF output, that's a performance measurement. Bit error rate, that's a performance measurement. Output power, that's a performance measurement. Spurious and harmonic outputs. These are all performance measurements for equipment. That's why equipment has been failing prematurely, because all of the measurements taken in factory tests are related to performance and not reliability. I think over the decades we kind of hoped that there was some relationship between if the equipment was functioning normally during test, that meant somehow it was going to last like it was supposed to, and it just doesn't. There's actually no relationship to performance and reliability. And so the existing space vehicle paradigm is presented pretty much in the Mill Handbook 217 or updates of it, which is the reliability analysis. And we call everything that's associated with the military handbook with reliability analysis engineering. All of the tools that's used to understand equipment performance and reliability, we call that diagnostic data. And diagnostic activities, that's things like doing equipment failure detection, isolation, and recovery activities, failure analysis, root cause analysis, data trending, equipment troubleshooting. Those are all reactionary kinds of things that you do after a failure has occurred to help you understand what happened in the past with great certainty. And what we're talking about is including things like part screening, where you screen the parts and test them, operate them for a while, trying to do a little burn-in and get the poor reliability ones to fail prematurely, including the three-stage qualification and acceptance test program, and even quality control improvement programs. These are all part of what we call the diagnostic tools that have been used. What we want to bring about is the tools about prognostics or prevention. When you no longer have equipment that fails prematurely or surprisingly, you don't need diagnostic tools. If the equipment's not going to fail in a surprise manner, you don't need these kinds of things, and it kind of makes them obsolete. And that's really our goal. And so this is a chart that's developed by Weeble to try to show how, when you deal with probabilistic requirements of reliability, how you can never achieve 100% probability requirements. These are the curves that's used to quantify the quality of the parts that you buy. And assuming that you have an 85% reliability part, this is the cost over here, the cost function. The cost to increase the reliability off of this 85% reliability goes to infinite. You can never achieve 100, when you're dealing probabilistic results, you can never achieve 100% no matter how much money that you spend when you're dealing in probabilistic results. And that's why it's such a paradigm change when I talk about 100% reliable equipment versus probabilistic results, that you can never achieve 100. And so it causes people to doubt that it's even possible, because they understand this relationship, that you can never do enough, you can never spend enough money when you're dealing with probabilistics to ever achieve 100%. And so it's very confusing. I talk about measured reliability versus probabilistic reliability. Two completely different terms. So this is the current AFSMC space vehicle procurement paradigm. We are now paying companies to produce equipment that fails prematurely. We're one of the very few industries that continue to do that. If you're in the consumer electronics products and you're producing products that fail prematurely, hey, that's out-of-pocket costs. And so it was those companies with out-of-pocket costs that developed the ability to identify the products that were going to fail prematurely, so they wouldn't ship them to the customer. And so with the AFSMC procurement process, they are still stuck in the old paradigm of continuing to pay companies to produce space vehicles that fail prematurely. And so they have these companies now, the Boeings, the Orbital, the Lockheed Martin. When you say, hey, we can now produce equipment that doesn't fail prematurely, their response back to us is, we don't have to. All of our contracts say we get to produce equipment that fails prematurely. And they're right. And so they have no motivation to change what they're doing until the customer, the Air Force, the military, whoever, the Navy, whoever's buying satellites, decides to change that reliability requirement from a probabilistic one to a hard remaining usable life. Or one that says, in the test data, there will be no accelerated aging. You ship only equipment to the launch pad that has no accelerated aging, no prognostic markers, no failure precursors in the test data. That's another way of stating it. Because what's happening is the equipment that's arriving at the launch pad, both from the equipment supplier and from the vehicle integrator, has got this data in the test the data that indicates the equipment's going to fail prematurely. And so this is an example of one of the companies, Sun Microsystems, now Oracle, they're high-end computer servers. They've added 1,000 analog telemetry sensors to both their hardware and software so that they can predict the equipment, the onboard equipment is going to fail in these things. You know, when the fan's going to break, when it's going to fail, when the hard drive's going to go, when any of the motherboards are going to go. They've added 1,000 analog telemetry sensors. A lot of satellites and rockets don't even have 1,000 telemetry sensors. That's an indication of how important this technology is if you want to produce equipment that won't fail prematurely. So this is a picture of the PHM satellite that just got launched that failed prematurely. The Apogee engine wouldn't work. And so what happened is the control electronics on the AEHF satellite built up here by Lockheed, it shuts off the Apogee engine after it starts firing. The data that it's getting from the satellites, it's indicating that there's something wrong. Now how can that happen? And how can that get past acceptance testing and get sent on to launch? It can do so because during the time that they looked at the data, the equipment performance was good. Everything was working fine. Remember what I said, in the measurements that they take and test, it's all performance related. They don't look to see if any of the equipment data has accelerated aging in it. So by the time this thing got on orbit, whatever part, at least one part that had accelerated aging in it, it had aged so much that it changed the behavior of the circuit. The timing circuit, the summing circuits that was bringing in the data to determine whether everything was okay on the satellite. At the factory, the equipment ran just fine. But once it got on orbit, again, those parts aged and it caused the, I'm saying likely, the failure analysis hasn't been out yet, but I'm giving you as an example of how that can happen. That is the part, there is at least one part in the control electronics for that Apogee engine that is suffering from accelerated aging, changing the performance of that circuit that was used to control the Apogee engine on the satellite. So this particular satellite was only about $2 billion because it was the first model. The other ones are cheaper than that because of the recurring costs, the way the non-recurring cost goes down. But this one in particular was $2 billion, and it was put through the acceptance test program twice, hoping that what happened on orbit wouldn't happen. This is why I want to mention that why AFSMC required space vehicle suppliers and the adoption of reliability analysis engineering way back in 1960. When reliability analysis engineering was adopted back in the 60s, it wasn't because it was the right thing to do. It was just a thing that it was the best idea that anybody had at the time. And so, you know, this has been now 50 years, and some progress has been made, and some new understanding has occurred. And so we want to change the reliability analysis engineering using a probabilistic results to a equipment that won't fail prematurely. The basis of reliability analysis engineering is the Markov property. It says that behavior is random and instantaneous. Remember what I said about failure precursors and prognostic markers. The reason that this transient behavior isn't recognized to exist in the space industry is because the Markov property prohibits it. If you believe that the Markov property is true, no behavior from previous is related to the behavior now. And so, since reliability analysis, or the results from reliability engineering, is used throughout the space industry, what we think happened is the reliability guys, that the belief that equipment failures are instantaneous and random leaked into the thinking process of the engineers who adopted that, who now today agree that equipment failures are instantaneous and random. Prognostic technology just simply recognizes, it doesn't recognize the Markov property. It says that behavior in the data way prior, up to a year before the failure occurs, is related to an event that happens up to a year later. That's what prognostic technology says. And it requires the development of a whole technology just to overwrite the fundamental belief that equipment failures are instantaneous and random. So what our suggested paradigm is, we want to have a reliability meter. Our algorithms work as a reliability meter. You hook it up to the equipment, it will measure the remaining usable life of every unit that has telemetry available from it. Any kind of performance data. It will tell you, if it's greater than a year, it says it will not fail from a premature equipment failure. If it's greater than a year, it means it will last at least 1 year with certainty. And so that's an all-new paradigm in reliability. So why is failure analysis and root cause analysis the wrong tools for producing equipment that won't fail prematurely? This is a chart that is time-based time base down here. This is the functional performance of parts inside of a circuit. These are transistors, capacitors, resistors. This is meant to be the degradation in life of a part, as the parts age in a circuit, as power is applied, how these parts age. This down here is meant to be telemetry data coming off of this, any kind of test point data, any kind of analog data. This shows how the data is performing. What happens is in this where these aging parts are going, if this part here may be the part that's aging the fastest, and it would age such that it causes a first transient behavior in the circuit. Now, it continues to function just fine and age as it was. But the transient that occurs in the circuit affects the aging characteristic of other parts. And in this unit here that fails, this is the part up here that actually fails. But this is the part in the circuit that actually caused the first transient that caused the failure. In the factory, we break open and we replace this part. And we put in a new part, we button it back up, put it back on the spacecraft, operate it, and then the next part will fail. We take it off, we rip it open, we replace that second part that fails. We do this 4 or 5 times. Finally, material control guys will say, gee, I guess the reliability, maybe at the 4th or 5th time they'll say, I guess the reliability of that unit's been compromised, so let's scrap it, okay? But it takes 4 or 5 times for that to happen because this equipment, space vehicle equipment, is so expensive, they don't want to throw away, they don't want to waste taxpayers' money and just willy-nilly throw it away. What this says is that the part that fails in a unit that fails is not the part that caused the failure. Even though you break it open, you find the part that's failed, up till now we concluded, oh, that part is the reason why it failed. No, the reason that this part has failed is because the unit is failing. After this part fails, this part's going to fail, that part's going to fail. That part that you found that has failed in a failed unit is not the cause of the failure. And that's why when you do a failure analysis and you do a root cause analysis, you're looking at that one part. That's not what caused although the unit did fail to function because this part no longer functions, it was this part over here that drove that one to fail. And this part, the aging characteristics of that part is going to force the other ones to continue failing. And you end up with equipment that fails serially. It can fail 4 times, get buttoned up. If it happens to make it through the next series of tests and gets on orbit, then it fails. And that's what I've demonstrated here today, is how those things happen.
So you're talking about baselining circuit boards and individual electronic components to look for nominal behavior, and then you go and look, then you can take that pattern analysis and look at... we don't work at the part level. There are organizations that look at the part level. We find it at the assembly level, or the box level, or the board level, if we have access to test point data or any kind of analog data that's available. But the equipment has to be running, it has to be collected, the data has to be present. There are companies organizations, NASA Ames up at Moffett Field is trying to find the algorithms to identify at the part level which ones are going to be failing prematurely. We work at the assembly board box level and vehicle level. Because we find the same data that at the part level, only we find it at the unit. It would be nice to be able to spot a part and throw it away and realize, but that's too expensive and too costly. We do it at the unit level, and that seems to be acceptable.
So you're saying you get that stream of data across the bottom of the
Yeah,
chart?
right. And so this would be we look for this first transient. From this first transient, we can then predict the remaining usable life based upon the 30 years of doing this. These are the other transients that occur that are triggered by this part that's got the highest degree of aging characteristics. We look for all these transients. And this behavior is never reproduced. You can't use pattern recognition software to find it. If you see it in one unit, you can't use that behavior to find it in another one. The variability in the parts in the circuit is such that you never see this kind of behavior twice. And that's why you can't use pattern recognition. Now, let me say in aerospace equipment. In the consumer products who are building thousands and millions of units, they do come up with failure models that they do embed into failure pattern recognition software. But in the aerospace and defense industry, we're fairly low volume. And so it doesn't work for us. And so we assume that you never see the same pattern twice. Our tools that we develop is for the onesie-twosie design, low volume kind of equipment and vehicles. So in reliability analysis, they use the bathtub curve to try to conceptualize the rates at parts that equipment fails prematurely at the beginning of life over here, and then this is at the end of life, and hopefully you don't have very many during the normal lifetime failure. When you switch to a when you eliminate the equipment that fails prematurely right here, all these failures that occur right here, you switch from a bathtub curve to a hot tub curve. Okay, we call that a hot tub curve. And you end up extending when you're working with equipment that doesn't fail prematurely, you extend the usable life. But what you end up with is a whole bunch of stuff failing at the end of life, which will take it out. But by working with equipment that doesn't fail prematurely, you get in a large population of vehicles or systems, large population, you end up with an increased usable life. Yes?
So you guys don't know when that first transient occurs.
Right.
So you're saying that you're measuring that, so if it's on orbit and a transient occurs, all you can do is tell someone, hey, your thing's going to fail most likely in the next year because a transient has occurred. But you can't tell a satellite company, hey, this vehicle you're about to launch is good to go because there's been no transients.
That's what we do. We do that.
But then if right after launch a transient occurs,
then that unit then has, we will then determine how long its remaining usable life is, and it wouldn't be no more, we're only valid for a year. So knowing that equipment's going to fail from once you get on orbit, knowing that you're going to have that failure, you can react to it. What we're saying is, if you identify all of the equipment with premature aging in the factory, you will not, the likelihood of having one right after launch is pretty slim. Once you're starting to work in the 100% reliability domain, the whole paradigm changes, and that's why you get an increased usable life down here once you start eliminating. The likelihood of something getting a transient right after launch is, it's there, it's something, but it's pretty low. But this is a lot better. What we're talking about doing is a lot better than what we're doing right now. It's not, according to Aerospace Corporation, and both military and commercial space missions have a 25% infant mortality rate within the first year. 1 out of 4 military programs will not be functional within 1 year that gets launched. Either a combination of launch vehicle failures or on-orbit satellite failures. And that 25% is even in the commercial space industry. And they do almost exactly the same thing that NASA and military space does in terms of testing. They do virtually the same thing. And so that's what we're trying to do. We're trying to take that 25% failure rate, maybe knock it down to under 5% is what our hope is. 2 or 3 or 4%. Because there are still some failures, for instance, some launch pad, there are some things that can occur from the launch pad that will cause a failure, those kinds of things. So there are still going to be some things that are going to occur that we don't fix. But you're going to take from a 25%, maybe hopefully down to under 5. And when a satellite is $2 or $3 billion each, including the launch vehicle and stuff, it's quite a savings. And so, from the awareness gained from adopting the prevention paradigm, what we're talking about, rather than the reactive paradigm that we currently have, 3 things happen. 3 things you learn. If you're going to test to measure, if you're going to test equipment, you're testing to measure equipment performance. And that's very important to do, because there's performance specifications that the contractors have that you have to meet. And so it's important to measure the performance of the equipment. But if you're testing equipment, you have to realize that you need to add in a measurement related to the equipment life, and that's what we offer in our technology. So people already measure the equipment's performance. We want to measure the equipment remaining usable life, and then the third one, which is pertains to the latest GPS satellite, the one that launched a payload that didn't work. The way that they decide a subsystem design is all performance based. In order to make sure that a subsystem is going to be interoperable with other systems already on orbit, you need to test for interoperability. Is it going to be interoperable, not does it meet performance requirements? So what we're saying is measure the test, measure the performance and test, measure the reliability, and oh, by the way, if you want it to be interoperable, you've got to come up with measurements to make sure that it's interoperable. And so here's an example of what we find in our test data. This is for a gyroscope on the Hubble Space Telescope. Gyro A, Gyro C, Gyro B. This is what we identify as prognostic markers, accelerated aging, failure precursors. This time scale is proprietary. But it's under a year. Most commonly, we are able to identify remaining usable life of about 5 months. Once we identify this behavior in the data, it will often operate until at least another 5 months before it fails. Here's some more examples. This is just the same data, standard deviation and the mean, how it's reflected in all of our standard tools that we use in diagnostics as well. And here's another one where the motor current on another gyro changed behavior that we identified, and it failed when we said it was going to fail. Telemetry transmitters, same thing. RF transmitters, same thing. This is a solid state, a reel-to-reel tape recorder. They don't exist anymore. Yeah, right. Any questions? I want to get you guys out. Yes?
Wait a quick. So it sounds like the two benefits are 1 year on orbit initial, and then you guys give someone about 5 months to get their act together after the failure.
Yeah.
Instead of somebody guessing.
Right.
So are you guys doing any work on algorithms to extend out that 1 year?
We are, the way that, and our 1 year is based on actual achieved results. What we need to, instead of working in the millivolt, milliamp range of data, we need to get down to the micro milliamps, millivolts in terms of behavior that we're looking at. And we don't anticipate that happening anytime soon. So that is an order of magnitude that we've got to improve on our accuracy of the data that we're looking at. There was something? Yes, sir.
Okay. Question: if mission's already been on orbit and an anomaly did happen,
Yes. Yes.
And you did your diagnostics,
yes.
How does that affect your 1 year prognosis?
We do that too. That's what we do. When you've had an event, we will go back and look at the past data and show you where the behavior was that was missed by the engineers that indicated it was going to be failing. So we have those results in our database also. We have that type of analysis to do also. What we do is, when we come into a factory, because the space industry has never recognized transient behavior, we can walk into the production process and find the instructions in the test procedures telling the test engineers to ignore transient behavior and identify it and get it changed. It will be relaying right in front of the people. It will be the instructions to ignore the very data indicating that the equipment's going to be failing prematurely. Because the space industry has ignored the presence of transient behavior since day one, because of the Markov property. So it couldn't exist. If you want to use the Markov property, there's no such thing as transient behavior. That's related to equipment failures. Yes?
You're obviously working with existing telemetry. Is there any sort of change in the sensors or additional measurements that can be built into satellites that would improve?
Right. None of the systems right now have been designed to work with prognostic technology. Contractors often get to argue to cut out the very data that we use, telemetry. They'll instrument maybe about 90% of the equipment on board. We want them to do 100% of all active electrical and mechanical equipment so that the data will be available in future spacecraft. And the other thing that we want them to do is operate the equipment as long as they can while it's at the factory on the ground to collect that data. Right now they turn everything off in between tests and they're not running it to collect data because they're saying, hey, we've measured the performance. That's the only use that they're using the data for is performance, and then they just shut everything off. A third thing can be done is if you, instead of just one telemetry measurement, put in two. If you put in two in parallel, then that gives you more data related to the equipment behavior. You can isolate whether it's an instrumentation failure or whether it's the unit is failing. So there are some minor changes that need to be done in the system for future space vehicles to help improve its use with prognostic technology. But we work already, we're completely compatible with what data is available there already. And it's any kind of test data, not just telemetry. Our system happens to work with telemetry, which is really cool because telemetry is always available. But if there's other test data that's collected during diagnostic activities, we use that too. Any kind of test point data, any kind of performance data, we use it all.